Quadratic Inequalities, Lesson 1, One Variable. This lesson will focus on developing strategies to solve quadratic inequalities in one variable, modeling and solving problems using quadratic inequalities, and interpreting quadratic inequalities to determine the solutions to problems. We can have quadratic inequalities in one variable in one of the following four forms. So you notice that we only have an x variable in these questions, and we can have less than or equal to, greater than, or greater than equal to. A, B, and C are all real numbers, but A cannot be 0. If A is a 0, we no longer have a quadratic inequality. We can solve quadratic inequalities graphically or algebraically. The solution set can have no values, one value, or an infinite number of values. So to solve a quadratic inequality of the form, and this one is where our inequality is less than or equal to 0, and our inequality is x squared minus 2x minus 3 has to be less than or equal to 0. We're going to solve it both graphically and using roots and test points. To solve a quadratic inequality graphically, we first of all would graph the corresponding quadratic equation. So the corresponding quadratic equation would be x squared minus 2x minus 3. And we can graph that using vertex form, table of values, technology, any of those forms we've already learned about this year. If we want those values to be less than or equal to 0, so this is my function, is this parabola. I want to know when is that less than or equal to 0. Well, the only time that that is less than or equal to 0 is when that function is below 0 on the y-axis. And so it goes from any value in between -1 and up to +3. So our lowest value then will be -1, going up to a value of +3. So those are the values for x that will make this a true equation. I can also write it as -1 has to be less than or equal to x, and x has to be less than or equal to +3. We can solve it graphically, that was solving it graphically. To solve it algebraically, we're going to use roots and test points. To find the roots, we need to start by factoring. So to factor x squared minus 2x minus 3 is less than or equal to 0. So factoring, we'll factor into two factors, one that is x minus 3 and one of x plus 1. The resulting roots would be that x is equal to +3 or x is equal to -1. Let's draw a number line next, plotting those two possible solutions. So -1 would be here, +3 would be here. This breaks the possibilities for x into three sections. One where x is less than -1, one where it's between -1 and +3, and one where x is greater than 3. Our interval in this middle is less than and equal to or greater than and equal to because of the fact that our inequality includes 0. So at a value of -1, our function is 0. At a value of +3, our function would be 0. We now want to test points that fall in each of those intervals. So let's start by testing a value where x is less than -1. So we're going to test that x is equal to -2. To test for -2, we're going to substitute -2 into the original inequality. So we have negative 2 squared minus 2 times negative 2 minus 3, and we want to see whether or not that is less than or equal to 0. So negative 2 squared is 4 minus 4, plus 4, minus 3 is less than or equal to 0. 4 plus 4 is 8 minus 3, less than or equal to 0. 8 minus 3 is 5, which is not less than or equal to 0. So therefore we know that it's not in, our solution is not in that interval. Let's try now a value in between negative 1 and 3. So let's test x equals 0. This time we have 0 squared minus 2 times 0 minus 3, and we want to see whether or not that is less than or equal to 0. 0 squared is 0. 2 times 0 is 0, so we end up with negative 3 is less than or equal to 0. This one works. So I know that numbers in between negative 1 and 3 are part of my solution set. We should also test that third region. So I'm just going to, let's do it over here. So let's test a value that is greater than 3. So let's test x equals 4. We end up with 4 squared minus 2 times 4 minus 3, and we want to see whether or not it is less than or equal to 0. 4 squared is 16 minus 8 minus 3. 16 minus 8 is 8 minus 3, which is not less than or equal to 0. So the only range that works for this solution is between negative 1 and 3. And so again, we can write our solution one of the two ways that we did when we were graphing. Our next example is one where our quadratic equation has to be less than 0. So here's our quadratic equation. We're going to solve it not graphically, but by roots and test points, and then I'm going to show you an alternate method as well. The reason I'm not showing you graphically again on this one is because I want to focus on the algebraic solutions. So to solve using roots and test points, again, the first step was to be able to factor that equation. To factor it, it's always easier if our squared term is positive. So I'm going to take out a factor of negative 1. That will leave me with x squared minus x minus 12 has to be less than 0. I want to factor that. So that will factor into two factors of x minus 4 and x plus 3. Two possible solutions of x being equal to 4 and x being equal to negative 3. With roots and test points, our next process is to draw a number line. We have negative 3, and we know that our function is 0 there, and we have positive 4. So it breaks it into 3 sections again. We need to test a test point from each section. So from the first section, let's test x being equal to negative 4. If x is equal to negative 4, substituting into our original equation gives us negative 4 squared plus negative 4 plus 12 has to be less than 0. Negative 4 squared is 16, so this is negative 16 minus 4 plus 12 has to be less than 0. And we end up with negative 8 is less than 0, which works. So I know that the numbers on this side of negative 3 are included in my solution. We do not include negative 3 because our inequality says that it has to be less than 0. And at negative 3, the value of my inequality is 0. Let's check the next region. We'll scroll down. So we're going to test x equals 0 next. So testing x equals 0, I have negative 0 squared plus 0 plus 12 has to be less than 0. Well, 0 squared is just 0, so those two cancel out, and I'm left with 12 being less than 0, which does not work. One section left to test. So picking a value that's greater than 4, and I'm going to test positive 5. I end up with negative positive 5 squared plus 5 plus 12 has to be less than 0. 5 squared is 25, so I have negative 25 plus 5 plus 12 has to be less than 0. This gives me negative 25 plus 17 is less than 0, which is true. And so if I go back up to my number line, that means that all of my values greater than 4 are also included in my solution set. To write our solution, we have a couple of different options. The first option is to write it in interval notation. So we'll write it in here. In interval notation, the first interval is the one that's less than negative 3. So that means I can go all the way down to negative infinity. I can come all the way up to positive 3, but positive 3 is not included, and so we use a round bracket. Or I can also have the second interval, which is when all of our values are greater than 4. So 4 is the smallest one, going all the way up to positive infinity. Again, because it's not less than or equal to, I have to use round brackets. Another way of writing this solution is to say that it's all values of x, such that x has to be less than negative 3, or x has to be greater than positive 4, and x is an element of real numbers. Okay, let's look at another way of solving this. We're going to use something called sign analysis. For sign analysis, the first steps are the same. We want to get to this point where our numbers are factored, or our inequality is factored. To do a sign analysis, we are also going to draw a number line. We're going to plot those critical points of negative 3 and positive 4. The next step is we are going to list all of our factors. So we have factors of negative 1, a factor of x minus 4, and a factor of x plus 3. At negative 3, I know that x plus 3 is 0, because if I substitute in negative 3 for x plus 3 is 0. I also know that my function is 0 when our factor of x minus 4, if I substitute in 4 for that. Now what I want to do is look at each of these factors separately. Let's start with our factor of negative 1. All I'm worried about is the sign of that value. Well, it doesn't matter on the number line whether I go small or large. There's no x value here, so negative 1 will always be a negative value. My next factor. If I substitute in a value that is less than 4, because 4 is my critical one for this term. So if I put in something like 0, 0 falls in here. If I put in 0 for x in this bracket, I need to ask myself whether I end up with a negative value or a positive value. If I put in anything less than 4, I will end up with a negative value. However, if I put in a number that's larger than 4, such as 5, I end up with 5 minus 4, which is a positive value. My last factor, I need to look at numbers less than where it's 0, so it's 0 at negative 3. So if I put in negative 4 into this factor, I would end up with negative values. Anything larger than negative 3 will give me positive values. I now need to look at the overall sign of my quadratic inequality. My quadratic inequality is created by multiplying these three factors together. And so I can look at the sign in each of those intervals. When x is less than 3, this is the area that I want to look at. I'm just going to find a highlighter. So this is the section that I want to look at. When I'm doing that, I have a negative times a negative is positive, times negative means that my overall sign will be negative. Looking at the middle section, so looking at a piece in here, I have a negative times negative is positive, times positive means that my function will be positive. And in the last section, I have a negative times a positive, so my answer will be negative. Because my inequality asks me for values where it is less than 0, means that I want these sections where my inequality is less than 0. If it's less than 0, means that it's negative. So I'm looking for values of x where x is less than negative 3 and where x is greater than positive 4. And so there's my solution. And again, I can write it the same way we did the R solution by doing the roots and test points. Let's look at another example. So solving a quadratic equation in one variable. This one it says that 2x squared minus 7x has to be greater than 12. The first step is that we want to make it equal to, we want to make the inequality in terms of 0. So I want to subtract 12 from both sides. And we end up with 2x squared minus 7x minus 12 has to be greater than 0. Now this one throws a little bit of a curveball because of the fact that that quadratic inequality is not factorable. And so when one is not factorable, we now need to use some other method to find the possible roots. So we're going to use our quadratic formula. Remember that the quadratic formula is that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's substitute it. We end up with negative 7. X equals plus or minus the square root of negative 7 squared minus 4 times 2 times negative 12. Remember that all of that is under the square root sign. And over 2 times a, and a in this case is 2. Simplifying, we end up with x being equal to negative 7 becomes positive 7, plus or minus the square root of, simplifying underneath, we end up with 145 all over 4. It's hard to graph a number like this on a number line, and so we're going to approximate our values so that our calculations become a little easier. So x is approximately 4.8, or x is approximately equal to negative 1.3. The 4.8 comes from evaluating 7 plus the square root of 145 all over 4, and this one from 7 minus root 145 all over 4. Now we can do our test points again, or we could use the sign analysis. Using our test points, our number line, the values that we're going to put in here are our decimal ones. So we have one spot at negative 1.3 and one at 4.8. Now, I should have made those open circles because our inequality does not include an equal sign. So at 1.3, I should have an open circle, and at 4.8, I should have an open circle. I now want to test values in between each of those sections. So starting with a value that's less than negative 1.3, we're going to test x equal to negative 2. For x equals negative 2, we have 2 times negative 2 squared minus 7 times negative 2 is greater than 12. Negative 2 squared is 4, so I have 2 times 4 plus 14 is greater than 12. 2 times 4 is 8, plus 14 is greater than 12. This one is true. That means that this part of the number line is part of my solution. We then want to check a number in between negative 1.3 and 4.8. So we'll test 0. 2 times 0 squared minus 7 times 0 minus 12. Sorry, I substituted that into the wrong one. Let's use our original equation. Has to be greater than positive 12. 0 squared is 0, 2 times 0 is just 0, and 7 times 0 is 0, so I have 0 is greater than 12. This one does not work. Testing the last section, let's test x equals positive 5. So I have 2 times 5 squared minus 7 times 5, and I want to show that that is greater than positive 12. 5 squared is 25 times 2 is 50 minus 35, and I want to see if that's bigger than 12. 50 minus 35 is 15, which is bigger than 12, so this section of our graph works. And so this area is also included in our solution. When we write our solution set, we want to write it as exact values. So remember that this negative 1.3 came from this value. And so if we're writing it in function notation, we want all values of x such that x is less than that negative 1.3. So x has to be less than 7 minus the square root of 145 all over 4. Or x has to be greater than 7 plus root 145 all over 4. Our last question is applying quadratic inequalities. So if a baseball is thrown at an initial speed of 15 meters per second from a height of 2 meters above the ground, the inequality, negative 4.9t squared plus 15t plus 2 greater than 0, models the time in seconds that the baseball is in flight. During what time interval is the baseball in flight? So our quadratic inequality this time does not factor, and so we need to use the quadratic formula again. So substituting into the quadratic formula, we end up with negative 15 plus or minus the square root of 15 squared minus 4 times negative 4.9 times 2 all over 2 times negative 4.9. Simplifying, we have x equals negative 15 plus or minus the square root of, underneath that square root sign we'll simplify into 264.2 all over negative 9.8. Because we already have decimals in our question, we can change these into decimal answers, and so our time can be negative 0.13 or positive 3.2. And I got that just by simplifying this and using my calculator to give me the two decimal answers. If we think about what this means in terms of our graph has a negative a value, so we know that it's going to open down. We've just found our roots, so if we did a quick sketch, we would know that it crosses the x-axis over here at negative 0.13, and over here at positive 3.2, and it opens down. So it would be shaped something like this. So x is greater than 0 in all of this area. So we're looking for that time interval in between negative 1.3 negative 0.13 and 3.2 seconds. However, we can't have a negative time, and so our interval actually stops when the time is 0. So our smallest value for our time would be 0. Our largest value would be 3.2. 3.2 would not be included in our set, and so it would be a curved bracket. 0, the base value is not in sight at 0, and so it also would not be included. So I can write it in interval notation like that, or I can write that t such that t is in between 0 and 3.2. T has to be an element of real numbers.